What if I told you that the reality you know, the chair you're sitting on, the air you're breathing, even the thoughts in your mind, might not be as real as you think? What if the very fabric of our universe operates on rules so strange, so counterintuitive, that they've left some of the greatest minds in science trembling with fear? Welcome to the world of quantum reality, a realm where the impossible becomes possible and the line between science and nightmare blurs. Today, we're diving into why this quantum reality is what scares scientists. Buckle up, because this journey is going to challenge everything you thought you knew. Quantum mechanics, the science that governs the behavior of particles at the smallest scales, isn't just a theory. It's the most successful framework we have for understanding the universe. It's given us technologies like transistors, lasers, and quantum computers. But beneath its triumphs lies a dark underbelly, a set of principles so bizarre that they've haunted scientists for over a century. Let's start with the first thing that scares them: the very nature of reality itself. The observer effect. Reality depends on you. Imagine you're watching a coin flip. You'd expect it to either land on heads or tails, right? Now imagine that the coin doesn't decide until you look at it, and the act of looking forces it to choose. This isn't a magic trick. It's the observer effect, one of the most unsettling aspects of quantum mechanics. In the quantum world, particles like electrons and photons exist in a state of superposition, meaning they're in multiple states at once, like a wave of possibilities. But when you observe them, they collapse into a single state. This is called wave function collapse, and it's been proven in experiments like the famous double-slit experiment. In the double-slit experiment, electrons behave like waves when unobserved, creating an interference pattern. But the moment you try to measure which slit they pass through, they act like particles, as if they know they're being watched. This isn't just a quirk. It suggests that reality itself depends on observation. Albert Einstein famously hated this idea. He once asked, "Does the moon only exist when I look at it?" The implications are chilling. If observation shapes reality, what happens when no one's looking? Does the universe even exist without a conscious observer? This idea terrified Einstein because it challenged the very foundation of classical physics, which assumes an objective reality that exists independently of us. In quantum mechanics, there's no such thing as an objective reality, at least not in the way we understand it. Some scientists, like John Wheeler, proposed the participatory universe theory, suggesting that consciousness itself might play a role in creating reality. If that's true, then what are we? Are we just observers in a cosmic game? Or are we something more, something that shapes the universe itself? The uncertainty is what keeps scientists up at night. It's as if the universe is playing a game of hide-and-seek, and we're not sure if we're the ones hiding or the ones being hunted. Quantum entanglement, the ghostly connection. If the observer effect wasn't unsettling enough, let's talk about quantum entanglement, a phenomenon so strange that Einstein called it spooky action at a distance. When two particles become entangled, their states are linked, no matter how far apart they are. If you measure one particle, the other instantly changes to match, even if it's on the other side of the universe. This defies everything we know about space and time. In 1964, physicist John Bell devised an experiment to test whether entanglement was real. The results were staggering. Entanglement isn't just a theory, it's a fact. Particles can communicate faster than the speed of light, which, according to Einstein's theory of relativity, should be impossible. This phenomenon has been confirmed in countless experiments, including a 2017 study where Chinese scientists entangled particles and sent one to a satellite 1,200 kilometers away. When they measured one particle, the other reacted instantly. But here's the scary part. We don't know how this happens. Entanglement suggests that the universe might be fundamentally interconnected in ways we can't comprehend. Some physicists, like David Bohm, propose the idea of a quantum potential that links everything together, a hidden layer of reality we can't see. Others think entanglement might hint at extra dimensions or a non-local universe where distance doesn't exist. But the lack of answers is what scares scientists the most. If particles can communicate instantly across vast distances, what does that mean for our understanding of causality? Could the future influence the past? And if everything is connected, are we entangled with the universe in ways we can't even imagine? The implications are enough to make anyone uneasy. Imagine a universe where every action you take ripples across space and time, affecting things you'll never see. Imagine a reality where the boundaries of distance and separation don't exist. It's a concept that feels more like a ghost story than science, and yet it's been proven to be true. Scientists are left grappling with a reality that seems to mock our understanding of the world, whispering secrets we're not sure we want to hear. The many worlds interpretation, infinite realities. Just when you thought quantum mechanics couldn't get any weirder, let's talk about the many worlds interpretation, or MWI. Proposed by Hugh Everett in 1957, this theory attempts to explain the strangeness of superposition and wave function collapse. Instead of a particle collapsing into one state when observed, MWI suggests that the universe splits into multiple realities, one for each possible outcome. In one world, the particle is here. In another, it's there. In one world, you're listening to this right now. In another, you never found this script. The many worlds interpretation means that every decision, every quantum event, creates a new universe. Right now, there could be an infinite number of yous living out every possible version of your life. In one world, you're a billionaire. In another, you never existed. This idea is both fascinating and terrifying. Richard Feynman, one of the greatest physicists of the 20th century, once said, "I think I can safely say that nobody understands quantum mechanics." And MWI is a big reason why. If infinite realities exist, where do they all fit? Are they stable? And what happens if they collide? Some scientists fear that if MWI is true, it could mean our reality is just one of countless others, and we have no way of knowing if ours is the real one. Worse, what if these worlds interact? Could we accidentally cross into another reality, or could something from another world cross into ours? The idea of infinite, uncontrollable realities is a Pandora's box that many scientists would rather not open, but quantum mechanics forces them to confront it. It's the kind of thought that lingers in your mind late at night, making you wonder if the choices you didn't make are still out there, living a life of their own. At the heart of quantum mechanics lies the measurement problem, a puzzle that's been haunting scientists since the theory's inception. We've already talked about how observation collapses a particle's wave function, but here's the question no one can answer. What counts as an observation? Does it have to be a human? A machine? A cat? This ambiguity has led to some of the most famous thought experiments in science, like Schrödinger's cat. Owen Schrödinger proposed this thought experiment in 1935 to highlight the absurdity of quantum mechanics. A cat is placed in a box with a mechanism that releases poison if a radioactive particle decays. In quantum mechanics, the particle is in a superposition of decayed and not decayed, meaning the cat is both alive and dead until you look. This paradox illustrates the measurement problem. When does the superposition collapse? What defines an observer? And most disturbingly, what does it mean for reality itself? The measurement problem scares scientists because it suggests that reality might not be fixed until it's observed. Some interpretations, like the Copenhagen interpretation, say the collapse happens when a measurement is made, but they can't define what a measurement is. Others, like the many worlds interpretation, avoid the collapse altogether by proposing infinite realities. But none of these answers feel complete. The uncertainty gnaws at scientists, leaving them to wonder, if reality depends on measurement, what happens when we can't measure something? Does it even exist? It's a question that feels like staring into an abyss. The more you think about it, the more it stares back. The implications for humanity. Are we in control? The scariest part of quantum reality isn't just the science, it's what it means for us. If reality depends on observation, if particles can communicate faster than light, if infinite worlds exist, then what does that say about our place in the universe? Are we in control, or are we just pawns in a cosmic game we don't understand? Quantum mechanics challenges our sense of free will, our understanding of time, and even our definition of existence. Quantum technologies, like quantum computers, are already harnessing these strange principles to solve problems classical computers can't. but with great power comes great risk. Some scientists worry that as we delve deeper into the quantum realm, we might uncover truths we're not ready to handle. What if we accidentally alter reality itself? What if we open a door to another world, or let something in from one? The more we learn about quantum mechanics, the more questions we have, and the more we realize how little we truly know. It's a humbling thought, but also a terrifying one. If the universe operates on rules we can't fully grasp, then how can we predict what comes next? How can we protect ourselves from the unknown? Quantum mechanics forces us to confront the limits of our understanding, and for scientists, that's a deeply unsettling place to be. It's like walking through a dark forest, knowing there's something out there, but not knowing if it's friend or foe. Conclusion: the fear of the unknown. Quantum reality is a paradox, a beautiful, terrifying puzzle that has revolutionized our understanding of the universe while shaking the foundations of everything we thought we knew. It scares scientists because it forces them to confront the unknown, to question the nature of reality, and to wonder if we're even capable of understanding the truth. As physicist Niels Bohr once said, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet." So the next time you think about the world around you, remember, at the quantum level, nothing is as it seems. And that's what keeps scientists, and maybe even you, awake at night. Thanks for joining us on this journey into the unknown. If quantum reality scares you as much as it scares scientists, let us know what you think. And don't forget to like, subscribe, and stay tuned for more mind-bending explorations. Until next time, stay curious, but maybe not too curious.